Go ahead.
Okay, so I connected it, but didn't turn it on. Thank you. Again, so the separation between the first two lectures and the second set of lectures across the weekend, I mean, essentially is going to go from single polymer properties and its implications for network elasticity to intrinsically network or collective properties, okay? That's really the dividing line, although it wasn't what I planned, that's basically the dividing line between last week and this week. And I just want to begin by, because I was rushing a little bit toward the end, and I got some questions about this, so I want to begin with this argument about the naive initial expectation for a non-affine modulus. The basic physics is sort of sketched there, that if I do not uniformly deform every microscopic element within a network, I inevitably start generating bending of fibers. And models of this go back at least to 96, actually slightly before Satcher. I probably should have included another reference. Satcher and Dewey in 95, I believe it was, had a model for stiff biopolymer networks. But basically, those models gave a quadratic dependence on concentration, the argument for which I want to quickly go back over. But I also want to point out, this is actually a classic material science result. So anyone familiar with metal foams or other structures like that in a material science context, there's a lot of modeling that's been going into that for decades even before. So actually, the Croy-Fry paper specifically mentioned some of those earlier metal foam ideas. But the basic idea is the following. We're going to look at a linear response regime, so this will be appropriate for linear elasticity. And the basic idea here, I'm going to sketch this in terms of a lattice. It works off lattice if you put in average values for things like separation between crosslinks. But thinking of that as a lattice spacing, a non-uniform strain might look something like this. So let's say this structure is going to be sheared this way, and if this pair of segments doesn't quite deform the way these do, there'll be some relative angle between the two, call that delta theta. That should be proportional to the strain that I impose to linear order. So quite naturally, that should be proportional to strain. The bending would then be the curvature, I should say, would then be the ratio of that angle to the range over which that deflection occurs. Square that and multiply by the bending modulus, and that would be the bending energy per unit length. And so that gives you an energy which goes like gamma squared. Of course, it's going to be linear elasticity. The modulus will be kappa over LC squared. That's this term. But this is an energy per unit length now, so I multiply by the length per volume. And since this is proportional to concentration, and as I argued before, if you just replace this, well, if you think of it as a lattice, 1 over the square of the lattice spacing is also a measure of the concentration of this network. That naturally gives you 2 factors of concentration. At low volume fraction, I should have emphasized maybe last time, I think I did, but maybe I should re-emphasize. All those experiments I were talking about are typically at volume fractions of 1%, or usually even well below that. 0.1% would be typical. Milligram per milliliter is the standard range. Okay, so anyway, this certainly suggests that since this is a softer mode of deformation, this should win, right? If you deform a system, it'll look for the easy way out, right? And so it certainly suggests that this never happens, affine never happens, bend always dominates, but it's not so simple, because last time I pointed out that even the affine case, if you take into account thermal fluctuations, you get a much softer, over some parameter range, stretching response. That can dominate. That's a single polymer effect. But then otherwise, it certainly looks like this should be the dominant situation, at least if you remove those thermal fluctuations. So I'm going to turn off temperature for the rest of the discussion. Not quite. I probably will get back to it next time, in the next lecture. But certainly today, turn off temperature. We're in an athermal environment. OK, so let's see what happens. So there's a problem with this argument. There's a really basic problem. And that is the following. A lot of the fiber structures I was telling you about, I am particularly interested in, I would also confess, a limit in which is more of a fiber network rather than a lattice structure. And what that tends to mean is that those fibers can have very long-range mechanical effects that go well beyond the scale of the mesh, or an approximate unit cell size, let's say. And here's the problem that occurs in this affine limit there, because you see, by the way, it's important to note, this modulus through this argument depends on the bending rigidity of fibers. Stretch modulus doesn't appear. That literally means this deformation mode doesn't generate any stretching at all. OK, so nothing's getting stretched. But here's the problem. If I shear this system like this, and I got a fiber at an angle like 45 degrees, that's going to be a pretty unhappy one, right? Because it's going to, the deformation is going to want to stretch it. So I'll look at that fiber and turn it horizontal. So if that's and I want you to think of this sitting in a network where there's many, many crossings with other fibers. I'm just focusing on one fiber. How can I avoid stretching that fiber? So imagine affinely deforming the network, and the only way it's going to avoid stretching is to somehow contract again to its original length, right? So that's what I'm trying to illustrate by this contraction here. So this would have been the full extent. It contracts a bit. What does that mean for all these other fibers crossing it? Well, they start to get pretty radically bent, right? In fact, the amount of contraction here is going to scale as the strain imposed and the length of the fiber. So L is going to be my symbol for the molecular weight or length of the fiber, and you should imagine that that's, well, this argument is really for L much greater than the mesh size or cross-link distance. And that's a big problem, because that means that I'm taking a huge, in the limit of high molecular weight, I'm taking a huge section of the network and I'm deforming it massively. Not in a way which only depends on the strain, but also depends on the molecular weight. That means that even the bending energies associated with this get huge in the molecular weight limit, in the high molecular weight limit. So that ultimately means that the system will have to stretch if I go to high molecular weight. OK, so a more realistic picture is the following. I'll go down the arc length of the fiber from 0 to L, and just imagine labeling the relaxed, unstretched arc length. So that's the range of the fiber. You could imagine plotting the tension in the fiber. I'll call it tau. Well, in the fully non-affine case, if it can really fully relax the stretch, then of course this tension would be 0. But it won't be because of this mechanism. There will be some tension generated in the middle. It'll happen to be essentially flat in the high molecular weight limit. And then near the ends, if I balance the bending energy associated with all this deformation, I'll get a zone over which the contraction can occur, not over the full fiber length, but over a region. So there'll be a new length scale that appears. I'll call it L parallel. It's going to be a longitudinal length. And so this happens to be what also simulation shows if you simulate high molecular weight fiber networks, 2 dimensions. Or, well, let me hold off on 3 for a bit. Okay, so it's that limit of high molecular weight I want to address. And I want to go through an argument. It's not exact. It's a scaling argument. It's a useful starting point. It's not exact. I want to go through a scaling argument which shows a little bit more of the physics of why this is limited. Question?
Yeah. So how is the stress inside fiber?
Yeah, so this is the tension you'd measure if you were in the fiber. So,
Recedes at the boundaries.
oh yeah, sorry, it goes.
It recedes at the boundaries.
Yeah, it goes to 0 at the ends because imagine some little end here. Well, it's not connected to very much, so nothing is going to really stretch it. So certainly the free ends, so some dangling end on the fiber outside of a cross-link, so to speak, will be relaxed. What's the shape of this?
No,
Oh.
what's the shape? What's holding it?
Oh, all these other fibers. These are cross-links. So at some point, this bend is going to be too much, so that fiber will pull it back and start generating stress. And notice as I go deeper in from the edge, that tension's going to go up because I've got other neighbors which are pulling on it. You see that? So that's why it tends to grow at the edge, typically flat in the middle at high molecular weight. At modest molecular weights, it'll be more like a sine mode, okay? And it won't have a flat region, okay? And in the extreme case of low enough molecular weight, I won't generate any tension at all. But I'm particularly interested in the high molecular weight limit because there's some new physics there, okay? Okay, so confessions, yes?
Just one question. So then you wouldn't have the kind of dynamics that was Duchenne called rotation?
Oh yeah, so these are permanently cross-linked systems. I'm not allowing any motion of the center of mass of the fiber. You could actually, it's kind of interesting to imagine what happens when these cross-links themselves are dynamic. But no, I'm not allowing for any reptation. Obviously, if these were not fixed bonds, then the polymer could relax and just pull back within its deformed tube. That would be more the reptation picture. But I'm interested in the elastic limit. So again, these cross-links should be thought of as permanent. Okay, so I was just going to say confessions. I'm going to sketch, and in the interest of time, partially sketch the essence of an argument which gives you that length, that L parallel. Actually, it's not worked out in any of these references. I should point out, this is a useful reference for a number of the things I'll be talking about, not for material after 2014 for obvious reasons. This is with my former grad student, Chase Broeders, who's in Amsterdam. Actually, I will mention along the way a paper with our next speaker, Xiaomeng Mao. So this is the Mao of our, well, she's not here yet, but she's showing up, I understand.
She just arrived at the hotel.
Good, good, okay. And Tom Lubinsky too, by the way. So so at least 3 of the speakers here were involved in this. It was a fun collaboration. So the scaling arguments I'm going to give you are approximate, useful starting points, conceptual framework, not exact. I'm really excited about an excellent student, Sihan Chen, who has just worked out a full mean field theory. It is mean field, so it won't get non-mean field exponents. I'll have more to say about that later. But with the exception of that, it captures everything. Thermal, athermal, linear, nonlinear, and also we'll get into some of the critical phenomena that I'll get to later. But along the way, it gets some of these arguments more precise. So anyway.
I have a question. So you were mentioning that very quick understand that those big points there, which are those the crosslinks?
Yes, yeah. So this is a crosslink.
Yeah.
And there's many other fibers it's crosslinked to.
Right. Then this says that the number of crosslinks would modify strongly this new correlational band that you're...
Oh, for sure. The density of cross-linking controls this strongly, and that's what I want to derive, quasi-derive. I thought I was going to say, oh yeah, I won't have time today, but tomorrow for sure, I want to get into a little bit more of the direct connection to collagen networks, since that's been mentioned. In addition to this reference, we've been working with our experimental collaborators quite a bit over the years, fleshing this out into a really predictive theory for collagen network mechanics. And that's more in a biophysical journal paper a few years ago. Anyway, won't get there today, but just wanted to give you the references. I sent around the reviews of modern physics. I don't know if it was distributed, though. It was? OK, I just didn't get the email on it. Was? Wasn't?
It's online.
Oh, it's online. Oh, I see. That's why I didn't get an email about it. OK. Fine. So let's try to estimate this. So, OK, so as I said, this is not a rigorous derivation. Oh, one more thing I want to say about this. So this goes back to a very nice collaboration with my former postdoc, David Head, who's now at Leeds, and Alex Levine. Sadly, Alex Levine passed away this last summer. Many of us are, he's a great colleague, and it gives me pleasure to talk about something where he played an important, influential role. Yeah, unfortunately, it's not with us anymore. But we had great collaborations over the years, and this was certainly one of the ones that I'm happy to mention. OK, so how to get this? So let's imagine an energy, and I'm going to talk about a couple different energies here, but I want to think about the elastic energy associated with this deformation. So the first thing to note is that I'm bending a bunch of polymers. I don't know the scale on which they're bent. I'm not going to make a simple assumption that it's only this scale. So I'm going to introduce a new length scale here, which I want to extract self-consistently. Call it L perp. So again, the idea is L parallel is going to characterize something about the longitudinal range over tension propagation, you could say, in the fiber. L perp is going to characterize the range of the bending away from the fiber among the other fibers. And so I could estimate the energy here as follows. I could say, well, the degree of my deformation here, so this delta theta that appears here is also a delta U over LC. Delta U being this displacement, right? But the degree of that longitudinal displacement is actually this. It's big. Actually, no, this would be if the full fiber could relax. This contraction with this argument is going to be taking this length times the strain. And then I divide by 2 powers of the scale over which the bend occurs. That's going to be my L perp. And then I square the result. That's the bending energy associated with one of these fibers that's meeting transverse. But there's many of them. In fact, the number of them is this. I take the ratio, whoops, no, LC. Too many lengths running around. I'm trying to keep them straight. Hopefully not confusing you in the process. Yeah, so this is the number of these bent fibers at the end, or at least the order of magnitude of it. So that's the bending energy I generate in all these guys, all of them. Yes? Yeah, so this bend angle here is proportional to how much it's displaced divided by the range over which the displacement occurs. Here, I'm taking a range L parallel here, and I'm moving this point of that order. If that occurs over a distance of that order, then this combination divided by one factor of that would give me an approximate expression for the, not the curvature, but the angle, exactly, thank you. One more factor gives me the curvature, okay? You can, this is a scaling argument, so, you know, yeah. So this occurs, though, because the system is trying to save all that huge stretching energy from pulling the backbone, right? So I'm going to save a bunch of stretching energy there, which is going to be mu. That's the one-dimensional Young's modulus of fiber, not the spring constant, but its effective one-dimensional stretch modulus. I'll get mu. I strain that part of the fiber by gamma. So again, these displacements are all going to be controlled by the amount of strain I impose. So for the energy, that'll be gamma squared. So that's a one-dimensional energy per unit length. But of course, the segment that is strained is of length L parallel. Okay? So now if I balance these two energies, I think you can see what's going to go on. Because you know, when these two things balance, I'll get a relationship between L perp and L parallel, okay? So literally, well, it appears with a minus sign. Set them equal to each other in magnitude, solve. And so what I'll actually get is an equation like this. So where does that come from? Well, let's see here. So this overall goes like, just a second. I wasn't done here. There's a length L perp to these fibers, and I calculated an energy per unit length. So now notice what happens. I've got an overall 1 over L perp cubed, and I'm going to compare it with other stuff. So I'll solve, and I'll get L perp cubed is proportional to, well, take all the other terms to the other side of the equation, you get this. L parallel appears squared because I have 3 of them here, 1 of them there. OK. Now, I should define for you a new length. Hang on. That. Yes, question?
Yeah. I still don't have a clear picture of what you think is going on. Are we saying that it's finely stretching at the edges and not or?
Okay, so yeah, so what I'm saying here is once we realized that there would be way too much bending energy associated with these ends for a really, really long fiber to contract fully, then I have to accept that the middle of the fiber is stretched. So the middle of the fiber winds up being affine, effectively. And the non-affinity is governed entirely by these edges.
So when you have gamma and perp, it seems like you're claiming that they are affine. Because gamma is the affine strain.
Yeah, so again, that's basically, even the non-affinity is going to be proportional to the strain I impose, though. It's going to respond linearly to the strain I impose. To linear order. I mean, obviously, there'll be higher order terms. But to lowest order, it should respond linearly. And the point here, again, is this. So the transverse displacement of this cross-link, therefore generating a bend here, is not gamma times the distance between fibers. It's gamma times these potentially big distance over which the contraction occurs. That's why I have that combination.
There's a conclusion that you're ignoring, which is the strain over the affine stretch.
Yes, yeah, right. So why am I missing that? Well, that's not going to change. I'm just asking the question, how much contraction do I expect at the ends? You're right. I'm only focusing on the non-affine bit. And in addition, there's a bunch of stretching in the middle. You're right. So this is only one of the energy contributions. Now, there's another one too that's worth focusing on. What about these guys? You see, they are getting bent substantially, so it's basically this combination. Okay? So here's the question I want to ask. How does this length appear? You see, I don't know what that length is just yet. All I've got is an equation relating it to something else, which is still unknown. Okay? I want a closed set of equations to solve for L perp and L parallel. And the key closing equation, if you like, is to note that this guy bends, but it bends at the expense of deforming filaments it's connected to. So you see a sort of self-consistent argument's going to appear. What are those filaments? Well, they're filaments that are crossing at not 90 degrees to that, but at a typical large angle on average, right? Now, in 2 dimensions, this is one key observation about 2 dimensions, even if I cross at some odd angle, I can't just displace this node perpendicular to this filament in order to generate a bend. I can't do that without compressing this filament segment because it's connected to something else. Now, this is relating to the isostatic condition of Maxwell, which you've heard about, right? And I'll remind you of that in a moment. But the important thing about 2 dimensions, and so I'm going to go through this argument first in 2 dimensions, and then just tell you what happens in 3D in interest of time. But in 2 dimensions, these filaments are highly constrained. That means that for these bends to occur here, I've got to introduce some stretching and compression of additional fibers that they're cross-linked to. Okay, so what I'm going to do now is just calculate the bending energy of one of these. So take this fiber and calculate its bending energy. And now I multiply by L perp, because that's how much I have. And then there's another energy, which is going to be of this order. So mu gamma squared, I argued, told me the sort of longitudinal strain in this fiber. These fibers laterally on the sides of this fiber also get compressed about that much in order to allow for this bend. In 2 dimensions. In 3 dimensions, they don't have to. That's an important observation. And so I get basically a term very similar to this. But now, there are many of those, right? So that needs to be multiplied by the number of them, which is L perp divided by LC. So these are slightly different energies, but I can also look at where these 2 terms balance, so find a minimum. Where these 2 terms balance gives me another relationship for L perp.
Sorry, Fred, I'm confused about the sign for them to balance.
They're both, yeah, so all I'm really doing, so what I'm really doing is this. I'm saying I get an energy of this order and an energy of this order. I'm not necessarily worried about signs. When I balance, when I minimize something, I'm going to wind up getting the 2 of them being comparable. Okay, and so all I'm doing is really identifying where these 2 terms are comparable. Oh, I neglected to point out something about this length. So where I have a ratio of kappa to mu, remember the naive expression for kappa was was the Young's modulus, another E, not to be confused with these elastic energies. Young's modulus, A to the 4. The ratio of that to the stretch modulus, which is Young's modulus A squared, is of order A squared. So I could replace this so-called bending length with A. It's going to be a small length. I'm going to leave it different, though, because in general, some of those biopolymers I was telling you about are a little weird. They don't satisfy Euler elastic arguments. So I better leave bending and stretching as separate parameters. They're typically related by this, but not always. And so if I take the ratio of the two, because of the different units, I get a length squared, so I can define that as the bending length. This is actually something going back to Euler. If you ask the question, if I pin the boundary condition of a fiber at one end, and I put an arbitrary force on the other end, you can ask the question, over what range does a bend occur? It's that length. Okay. Now, okay, I have two equations. They're not degenerate. They're not equations, they're scaling relations. But you can treat them as an equation, as equations. And so I've got two of them. They're not independent. I can solve independently for L perp and L parallel. And let me just give you the results. So L perp winds up being avoider LC squared over L parallel. And when all the dust settles, L parallel winds up being, this is the harder part of the calculation, a 2/5 power emerges. It's not interesting, it's just mathematics. Sorry, that's unfair to mathematicians, but it's not a particularly interesting mathematics, let's put it that way. Simple algebra. Okay, now this is a general thing we should have expected, right? I'm claiming that a new fundamental length is going to come out of my network structure. If you accept that that's a local quantity, why do I say it's local? Well, if this stress relaxation is occurring right near the ends, independent of some affinely stretched region in the middle, if I double the fiber, this bit should remain the same, right? So it's something I should construct from local quantities, not a non-local quantity like the length of the fiber. And so the only length scales I have running around really are LC, the architecture of the network, and LB, what I get from my two parameters, stretching and bending. So of course this length should be, and I can write it many different ways, it's going to be a length I get from combining two lengths. It's going to be 1 times a ratio of the others raised to some power that I don't know. That's general. Now, here's where the scaling argument is a little bit wrong. The claim is this winds up being 2/5. There's a reason why you might doubt this argument. Let me just point out one of them. Notice this says that the perpendicular length is proportional, that's the length of these bends here. That should be proportional to LC squared divided by L parallel. This is a length I claim could get large, right? In fact, I'm going to find it gets really large for weak bending energies. So that is true. This length here can span many cross-linked fibers, just as I was arguing. If that's the case, then notice this length looks like it can become smaller than LC. That doesn't make any sense at all. Because if it's smaller than LC, why won't this just bend and leave the neighboring cross-links unchanged? Okay, so you can begin to see that there's a potential problem with this argument. A much better calculation of this there actually shows that this exponent should be 1/2. Okay, but you get the idea. I wanted to go through this argument because it shows that this non-affine limit of the shear modulus for a network is mechanically inconsistent with the high molecular weight limit. Something else has to happen, and it's this. So now, look at the implications of this picture, though. Okay, so again, don't take the arguments as exact, take them as sort of physical motivation for that picture. So now, if you accept that picture, then what this says is the following. The fibers Okay, let me just say, in what follows, because some of the plots I'm going to show you use a different symbol for this, and because this is really a very important length scale that comes out, I'm going to call it lambda, rather than distinguishing longitudinal and perpendicular. So that's, this I'll define as lambda. It's a non-affine length scale, so I could put a little NA on it. And it's an emergent length scale that comes out from the collective properties of my network, okay? So if that's true, then notice what that says. That means that the affinely deforming part of the fiber is a fraction of order 1 minus lambda over L with some coefficient. So in other words, it's basically telling me that in the limit of very high molecular weight, I get almost all of the fibers being stretched. Pretty surprising result, considering that the stretching energy is usually so much higher than the bending energy in appropriate dimensionless terms. Okay, so that begins to suggest the following. If I were to measure the shear modulus and divide it by its affine value, okay, so 1 would mean I have an affinely deforming system. If I plot this versus L over lambda, then as L goes to infinity, this ratio gets small. Basically, almost all the fibers are stretched, and stretched according to the macroscopic shear field. And so I should approach an affine behavior. Now that's again this much higher modulus, right? That's this thing. So I'm now saying that there's a network reason why this actually can be true, even though it looks like this should be much softer. This does not, this result right here is a lattice-like result. It doesn't account for long fibers. That's what's missing. But now, as I go to, so when that ratio is of order 1, then I'm learning that only a small fraction, half or less of the fiber is stretched. So then the modulus falls. So that down here I get some other behavior, and indeed it's softer. Okay, so here's here's the kind of analysis that this picture at least can suggest. So the claim is the modulus, the real modulus, should be, well, mu rho is the way I prefer to write that affine modulus, right? Stretch modulus times length per volume times some scaling function, like you've seen in critical phenomena, like you've seen in many things, and the kind of thing Jim Sethna was talking about, right? Don't quite want to call it a universal scaling function. That's at least suggesting a scaling function. And the scaling function should be should have as an argument L over lambda, where f of x takes on two different limits. When x is large, this should go to 1. And when x is small, well, some power of x to the beta, let's say. So that's just a hypothesis. Let's see if it works. Yep.
Does this argument change if you choose three dimensions?
Yeah, drastically. I'm getting there. It's actually one reason I'm belaboring this so much, because I'm going to conclude that in 3D, you might imagine none of this applies, but it still does. So why? Okay, so anyway, when this argument is small, this should be the bin-dominated regime, right? This is where my modulus is far below the affine value. I should recover this result over here. But notice that this lambda here, so LB is the square root of kappa over mu. LB appears in the denominator here, and with that alpha. So let's track the dependence on kappa. Well, it's actually going to be kappa to the minus alpha over 2. Do you see that? LB goes like 1/2, kappa to the 1/2. I raise that to the power minus alpha. So notice that indeed this length goes to infinity for soft bending, okay? But we know what the modulus here is in the limit that L is much less than lambda. It should be the non-affine one proportional to kappa plus other parameters. The only way I'm going to get a kappa here is if this power together with that power combines to give 1. Do you see that? So literally, yeah, so lambda depends inversely on kappa. This is a negative power. But of course, this is plotted in the denominator here. So that all tells me that beta times alpha over 2 should be 1, i.e. beta is 2 over alpha. I claimed alpha was about 2/5. That would mean this would be of order 5, or about 5. I shouldn't use order of magnitude for a exponent. That we're not doing astrophysics here, okay? So this should be 5. A more precise value turns out to be 4, okay? But the point is it's a big power. So this winds up being 4. Does that work? Well, sure enough, you can put a line on this log-log plot for that range there, and you'd see an exponent of about 5, okay? It happens those data are not really in the asymptotic regime just yet, and so it's apparently about 5, but not exact. And again, this was from wonderful collaboration over the years. Many papers related to this, actually, with Alex Levine. Another interesting story about this. So Erwin Frey, I mentioned his name before in connection with that earlier model of the non-affine modulus. He's in Munich. He's another colleague who's been working a lot on this sort of thing over the years. And we had a nice collegial competition going on here. We found out about each other's work, and we decided to submit our papers simultaneously in our letters acknowledging the existence of the other paper, and it worked out nicely. They were both published together, back to back. So in the same issue. Now their interest was slightly different. They were focusing a little bit more on the critical phenomena associated. So this ultimately has to go to 0. It has to go to 0 because if I shrink the length of the fibers, at some point they're not sufficiently connected to even satisfy rigidity percolation. They happen to be more focused on that regime than we were. We were interested more in the transition to the affine. But we had essentially overlapping results that agreed nicely with each other. Very nice story. Yeah?
Yeah, you said that you wouldn't call these scaling functions universal. Why not? I'm just wondering if
there is some dependence on the architecture of the network. So this is a little bit more technical detail than I wanted to get into. You will see some discussion of that here. 2D is a very special case. And it's a very special case basically for the reason why you might doubt this entirely in 3D. Okay, you might think this is entirely a 2D result. So if you don't mind a little bit of a digression, in 2D, think about the Maxwell argument. So if I look at one typical node in a network, it has a number of degrees of freedom, which would then be D, the number of dimensions I'm in. And I would subtract off from that for every, now this is a central force picture with just spring constants. But I would subtract off from that the Z, or Z, depending on where you come from, neighbors that you have at a typical node, divided by 2, because each one of these constraints is a half a constraint for the 2 nodes it's connected to. And this is 0 at ZC, a critical or isostatic coordination number of twice D. Now, in 2 dimensions, that's 4. And 4 is exactly the kind of local structure I expect in a network. I've got a crossing point of 2 fibers. In 3 dimensions, that coordination number would be 6. Now, so one way to look at this is the following. So I can replace these by fibers that resist bending as well, but they're going to resist it weakly. If I tell you that the modulus has gone to an entirely affine modulus, which, by the way, is proportional to mu, that means fundamentally the elastic energy in the system is stretch. That suggests that I should be able to account for that mechanics with central forces, right? Stretching energies. And it's happening at the high molecular weight limit where L goes to infinity. And as L goes to infinity, I have many, many crossing points of a fiber with very few dangling ends. If this is a dangling end with nothing connected here, it's not really relevant. And so this corresponds to a connectivity of, or a coordination number of 3. So on average, the coordination number you'd expect to be 4 minus, again, some number to be identified having to do with the architecture, LC over L. So as the fiber gets really, really long, I go to coordination number 4. That certainly sounds consistent with Maxwell, right? So maybe this transition, and by the way, it's not a thermodynamic transition, this is just a crossover. It's literally a crossover from a non-affine regime to an affine regime. Maybe this is just happening because of that argument. If that's true, then it should never work in 3D, right? But I still have this argument. The actual formulas here change, but the same thing that I started with still applies in 3D. In 3D, I'm still having to, if I've got a really, really long fiber and it's going to contract and avoid any stretch, it's going to bend fibers around it like hell in the high molecular weight limit, right? It's not clear what happens in 3D. And there was a fair amount of debate going on after some of these results. And in particular, I want to acknowledge, well, one of these co-authors on this thing was Tom Lubinsky. And Tom Lubinsky and I certainly argued this point a fair amount about 10 years ago. But this argument there certainly suggests that it should still apply in 3D. So something is apparently wrong with applying this Maxwell idea. And I thought that was connected to your question. Is it? Or did I get too far away afield?
I was just wondering about universality.
Yeah.
Why wouldn't it
Thank you.
expect it to be universal?
Exactly. So here's the problem. This function definitely changes for different architectures. So that's why I don't want to call it universal. So if I simply go from a lattice structure in 2D to a what's called Mikado. Mikado is like the game. You just throw down rods at random in 2D. the Mikado model has junctions which can be really, really close or far apart. That distribution of cross-link distance, because of things like this strong inverse dependence on cross-link distance, that affects things, okay, if that distribution is broad. So anyway, the network architecture does appear, so that's why I would not call it universal. Yes?
And so the problem with the 3D is that you don't get three fibers crossing? I'm missing.
Yeah. Oh, sorry. I'm assuming the same local structure. In fact, actually, fibers crossing is even harder in 3D because they have more directions to avoid each other. Okay, that's another point. But when fibers cross, I'll show you some network architectures in a moment, but you know, it's at most 2 fibers crossing, occasionally a dangling end, so 3. So in other words, the connectivity of a fiber network in 3D should still be between these 2 limits. And that's nowhere near connected enough to have a central force network,
And there's no way
according
to
to
think
Maxwell.
about it as sort of a superstructure which acts like a node?
So something does happen a bit like that here. When these get so close together, they effectively collapse. But these are rare events. So you could say that this looks like a z equal, 6 connectivity point, but they're rare. So it won't, I mean, literally the average connectivity, whenever anyone measures it for a lot of these fiber networks, it's around 3.5. Never gets anywhere close to 6, except in special architectures.
But we know that, so yeah, when you do get rigidity.
Exactly, and I'm going to try and explain why.
Right.
Okay,
Yeah,
yeah.
when you have the Maxwell argument, you have to count for the bending constraints. And all.
Well, yeah, so a couple. The Maxwell argument is for central force only. It doesn't apply with bending, and you're right. And I don't want to go through what happens to the right counting here with bending. It's an appendix in the paper with Xiaomeng and Tom. So yeah, it's complicated. So what's going on in 3D? Well, this is key. And I'm going to conclude that there is an affine limit in 3D in spite of this, and a pure stretch regime, okay? And it's because of this physics. Yes?
Is it possible that there is another characteristic length in new direction in 3D?
It's a little hard to see it because all these lengths here still apply, and there isn't really an additional one. I mean, depending on the architecture, you could imagine something like a network which is sort of like a lattice, but has lattice spacings LC and twice LC or something like that. But I would say they're the same length, effectively. Okay, so here's what's happening. And here's why we strongly believe that this should apply in 3D. And it's the following. What does this say about Maxwell? Well, notice this goes inversely in lambda. Lambda, I've just said, goes like kappa to this power, kappa to the minus alpha over 2. Notice that as kappa goes to 0, this length, lambda, diverges. Oh, sorry, it's in the denominator, so I should put a plus there. So as kappa goes to 0, continuously from finite values, I go to the left extreme of this figure, and the modulus is small. It's an order of limits argument. It's not Maxwell or not Maxwell. It's an order of limits. What this says is no matter what kappa is, as long as it's non-zero and finite, could be as small as you like, there is a molecular weight beyond which stretching only occurs. It might be a huge length, but it's in principle there. Whereas in the other limit, if I take kappa goes to 0 first, then I'm over on this left-hand extreme to begin with, and I never move to the right. I never get a stretch regime. So again, the point is, it's not whether or not this argument here is correct. It's essentially, if there's any finite kappa at all, there will be a high molecular weight affine regime. Okay? So let's see how that works. Took us a long time to address this issue, and again, So this is just to show you again, local structures, those are from collagen, branch points, crossing points, connectivity, if you like, or coordination number would be about 3.5. Here's the 3D results. And another friendly competition was going on here. This started with some, well, not started. Obviously, it was an obvious question after something was seen in 2D, whether it applied to 3. But again, my student at the time, Chase Bruders, and also Tom Lubinsky and his postdoc, Olaf Steno, whose name you've seen before, I think. We again found out about a couple of very similar papers, and we submitted them simultaneously again. This shows what happens in 3D, and notice that what's plotted in the upper left-hand is, again, this ratio, G to G affine. You could say G to the stretch regime. And it indeed goes for high molecular weight to 1. The different curves are for different values of kappa, so it's not being plotted this way. That appears on the next plot. All the data collapse on this not universal, but scaling function. And in here, and in this case, the slope is 2. So this beta winds up being 1 in 3D. Sorry, alpha becomes 1 in 3D. So now these are mean field results. I can't guarantee that this exponent is exactly 1/2, but it's approximately 1/2. Here too, it's at least close enough to 1 we can't distinguish. And so these exponents differ, but this kind of formula still applies. And again, this is not in any way inconsistent with Maxwell. It's just saying that if there's any bending at all, that completely changes Maxwell's counting argument. And no matter how small kappa is, there's going to be a molecular weight. If you exceed it, you get a stretched network. Now, this was precisely why it was so hard to get to. In 3D, it was a bit of a stretch, I could say, so to speak, to actually get there. But it was doable. We did it. We chose to do it on a diluted particular network, basically based on an FCC. The nice thing about that is it's really scalable. You can make it as large as you want. Those are technical details. Tom and Olaf were using a unit cell, once we dilute that FCC structure, you get a random network that has no unit cell, and even though it has a local structure, which is admittedly anisotropic, there's no local cell. You can scale it up to arbitrary size and get distinct random structures. The unit cell doesn't quite permit that, and so they were not able to go to as high molecular weight, but the results are still basically consistent over the range they can get. So anyway, that addresses, perhaps surprisingly, that this regime here is still relevant in 3D, even though actually multiple people had argued that this basic consideration right here for a fiber structure with crossing fibers meant that you could never get a central force regime. But again, it's a subtle question of order of limits. Okay, so I would say we now have 3 distinct network regimes. We have the possibility, even in an athermal system, provided the molecular weight's high enough to achieve this high value of modulus. You can also get typically a lower value if you go to smaller molecular weights. And we have that thermal mechanism I mentioned before, which basically takes this and softens it by thermal fluctuations. Yes?
One last thought. If I took a network and instead of making it random, I made it polarized, in some sort of along the maximum extension axis,
some sort of ordered structure, yeah?
Yeah, then I could immediately go to stretch.
Oh, yeah, so by the way, this is a point that is very relevant to all these simulations. I should have pointed out that that is simulation work, but you can imagine, although I would say now we've got a good mean field that agrees beautifully with these results. It's very important, if you have a single fiber that spans your system, then that, in the limit of really soft bending, that can utterly dominate the mechanics. So what we actually ensured in this network was that no single fiber spans the system, so that whatever mechanics you see is not the result of spanning fibers.
But is that?
But I think what you're thinking of is a spanning fiber, right?
Yes. And
Yeah.
I guess the question is, we've been working on that question. Is that interesting?
Well, so it could be, yeah, so you could either have a spanning fiber or you could have overlapping fibers like this, which certainly could be very relevant. I mean, that's probably what a tendon looks like, right? At least for a physicist. If these are connected, then that structure will certainly be mechanically rigid to that particular extension. So our focus was more on isotropic networks.
Right. But that would also change the scaling behavior.
Yeah, but I would say it really doesn't, it doesn't really relate to this Maxwell picture, because that Maxwell picture is, I think, most appropriately applied to either a near isotropic, lattice type structure or a random network. Yeah, I mean, I would say you can somewhat trivially get a mechanical response here, which is stretch, if you've got aligned systems. None of this physics here would apply, unless you start, worrying about the mechanics of the transverse bonds, et cetera. Okay, so what I wanted to, I think I have just 20 minutes, right? Oh, did we need to take a break?
We have 30 minutes. I was to you.
Coffee break?
We should not do a coffee break. We'll do a stretch break. Like a
Stretch break.
2 minute stretch.
Stretch break until 20 till. How's that? 5 minutes.
Maybe I missed something, but the reason why you say that L and molecular weight is comparable is if you think of a fixed LC, then if L is bigger, it means that we have more crossings and it's the same as higher molecular weight.
Yeah, so I'm particularly interested in a sort of continuum limit where the fibers are so long compared with the sort of local architecture length scale that a continuum theory can come out. And this is essentially a continuum theory. If you add back in the discrete size, there's an additional rigidity percolation transition that happens down here. The length has to exceed enough, the length has to be long enough so that there's enough connected fibers to have some rigid structure. Yeah.
Wait, so the molecular weight is not just standard for the length?
When I say molecular weight, I mean a geometric measure of it, length. Yeah, not kilodaltons or megadaltons or whatever.
Yeah, I mean, that's part of what we're, like in cartilage tissue, you have regions that are very polarized and very aligned. So that's what we're trying to understand. But, so I totally agree, it's trivial.
Well, at least there is a limit which is trivial. I'm not saying your system's trivial, but there's at least a limit which is
I
trivial.
mean, that's fine. I'm happy to do trivial things if they're relevant.
Yeah.
But like how all of the sort of rigidity percolation, how the scalings that you guys get in your isostaticity.
I wouldn't necessarily assume they apply to a highly anisotropic structure.
Right.
However, an interesting limit for you might be looking at the mechanics of what it's connected to, right? And there you could have some, actually Mo and I years ago looked at reinforcing elastic networks with a few fibers, right? You could imagine an aligned version of that, where I've got a soft matrix here and
Sure.
fibers in it.
Yeah, so that's an example.
That could be an interesting example, which would then be not so trivial.
Right.
I was just thinking of direct cross-links.
But in some sense, right, as you pull out all of the bends and you get your stretched network, don't you end up in that?
Oh, this is not as a function of strain. This is a linear response still.
I know.
I'm still not straining it.
Right, but once you strain out, once you go to really high strains, then at some point
Okay,
you're going to reach an effective material with that.
Yeah, so I'm just going to start talking, I think, tomorrow about the strain control transition. And it's important to note that that transition can occur with macroscopic strains as small as 5%, at which point you're not getting significant macroscopic alignment. Obviously, if it's occurring at 30, 40%, then yeah, you're already starting to get significant alignment.
Yeah.
So,
But then, you know, in some sense, can I think about the nonlinear response of your network as approaching a network that is polarized? You see what I'm saying? Like, so in cartilage,
yeah,
for example.
yeah, a high strain limit you could.
I could think about, you know, like if I think about the.
And all the transverse ones wind up being sort of mechanically irrelevant.
Exactly.
Yeah.
And so the idea then is to understand the function in this nonlinear limit. You essentially have to map onto sort of, if you, it's almost like I take the tissue, it starts off isotropic, I can compress it, you know, things kind of buckle, you strain it a lot, and then it ends up being, again, into the stretch, but not for the original network, more for a network like that.
Sure, yeah. Why don't we get back into that with the with the nonlinear? Yeah.
Predominantly LC and then factor, which might be linear.
Okay, so should I get started again? Okay. So, well, actually, I should have used the time to do some erasing. But I want to emphasize everything I've been talking about is athermal. However, this picture right here, if you start adding in that thermal suppression of the stretch modulus, the softening due to thermal fluctuations, it's only going to lower this threshold, right? Because this lambda here also depends, so it depends inversely on LB. So that means it goes down as I soften mu. So that means if I add thermal fluctuations back into the mix, I'll still get this picture. I'll just get more of the stretch region, okay? Because of a softer stretch response. And so one of the things you can do is go back to the thermal affine regime, which I talked about before, and add this not quite this effect. You have to do things a little differently. What you do is you take into account the thermal fluctuations of the nodes more consistently. And you will get a finite temperature and molecular weight dependent modulus. So that would be the realistic semi-flexible polymer network. That's one of the things that this paper does here. I won't go into that because it's basically, the physics is already sort of apparent here. Yeah?
On a simulation level, what would a thermal fluctuation mean? We're changing the bond lengths, or also, I know in the FCC, because of the coordination numbers.
Yeah, when I say thermal fluctuations, I just mean Brownian forces. Okay, so I'm not going to allow fluctuations of cross lengths or architectural fluctuations or even plasticity, which can also occur, by the way. When I say thermal fluctuations, I just mean I'll take one of these networks and I'll let them start fluctuating with different bending modes, and the nodes will fluctuate around, et cetera. By the way, that's an interesting thing. If there's time, I definitely want to get to that in tomorrow's lecture. We won't have time today, but it's actually an interesting question. You've heard lots, I think in the prior lectures, you've heard a lot about this Maxwell argument, right? I'm sure Xiaoming is going to tell us some more. Tom, I haven't seen his lectures, but I assume he talked about it.
He focused on topological mechanics.
Yeah, but the basis of that is starting from Maxwell, yeah. So just simply taking this picture here and doing it at finite temperature, you'd be surprised how little work there's been done on that, okay? And if there's time, I want to mention something we think is very interesting there. But that would be jump.
I also have a question concerning simulations. How much does this exponent depends on the details of your model? Because
The what of the model?
the details of your model.
Oh.
You could suppose that bending is possible, you could suppose that stretching is possible. There are several details that could be.
Well, so there's been remarkably little work in 3 dimensions addressing this question. It is harder than you might think. And so, you know, I'm biased, but I was impressed when my student then and, let's see, no, actually, he was just moving to Princeton for a postdoc at the time. We were actually at a KITP workshop in Santa Barbara. And so not only was Chase really an excellent student, but Misha was also just an excellent postdoc. And when the 2 of them were working together, I was struggling to keep up. I mean, they were great. The joys of running a group. Occasionally you have these combinations of people that just, yeah, so very, very productive collaboration between those guys. Anyway, what I'm getting at is when they did this, it was pushing state of the art. Even though I tend not to think of my group as a computational group, pushing state of the art on the computation side, it was impressive. And there's been very little extension of this since then. People have tried to do finite temperature work in 3D, but it's necessarily smaller molecular weights. Okay. So anyway, here's what I'm getting at. We've got these results, but we really can only claim that these results, and in particular, let's say this exponent, applies to what is fundamentally a disordered regular structure, a lattice. Would it apply to a truly random network? And that's one of the beauties of this latest thing that Sihan Chen has done. It shows quite clearly 2D and 3D are very different, and this alpha equal 1 effectively, and the consequences of that apply to arbitrary structures in 3D. It, I think, addresses your question. I should actually point out why 2D and 3D are so different in another way. So look, when two fibers cross, and if I were to pin them together, as we do in our systems, again, as I've said, I can't bend this one without compressing this one, right? Because they're so interconnected. But notice in 3D, there's no problem. Because once I put these 2 fibers together, they form a plane, and there's a soft mode in the other direction. So that's another reason why 3D is very different. And if you trace through these arguments, what you'll find is that this length here, if you go through these arguments carefully in 3D, you can convince yourself this should actually be LC. And as soon as that's LC, then you can basically come up with the appropriate alpha here. Or at least an argument that suggests that. OK. Anyway, what I'd like to do in the last few minutes is connect up this work with Maxwell a little bit more directly, okay? So I want to look at the implications of this a little bit more carefully. Okay, so the basic picture of this central force argument is that once I connect a system up sufficiently, then a finite modulus develops. Was there a pointer here? Thought there was. Okay, well, basically, I'll point with my finger and hopefully you can follow. This blue curve is basically showing that the shear modulus will increase from 0 from what is a floppy regime. So a little inset here will be a useful reminder. This is connectivity. This is the isostatic connectivity, this one, in 2 or 3 dimensions. And a shear modulus will tend to grow from that point. It happens to be a second order like phase transition, which is interesting. So it's critical with fluctuations, et cetera. Not thermal fluctuations, because we're still at t equals 0. But it's critical. Now, okay, so we could study that, and many people have studied that transition. Obviously, it appears in the jamming context quite a bit. Goes back to earlier models of rigidity percolation, et cetera. And a paper of Maxwell's that until recently physicists never read, I would say, which is unfortunate. I've run into mechanics. I was sitting in the airport at one point, preparing some slides for a talk, and this came up. I was preparing, and a woman was sitting next to me, looking over my slides apparently, and it turns out she was a mechanical engineer. She knew exactly what I was doing. Oh, cool. Yet another example of physics ignorance of things. Well, was Maxwell a physicist or an engineer? He was actually both. Anyway, I like that confusion, since my home is now chemical engineering for the first time. I like that porous boundary. Anyway, okay, so if I add bending to this system, though, we've seen that you can stabilize. And unless you do something like go to very high molecular weight, you're going to stabilize at one of these low moduli, right? So you get a picture like this. So bending rigidity winds up being, and by the way, that curve should look familiar. Magnetization versus temperature, right? Finite field looks like that. So very, very naively, I want you to think about bending as a field, like a magnetic field, without the symmetry aspects. Just think of it as another coupling constant and a Hamiltonian that winds up stabilizing a network, okay? So what we started to ask is what happens to this Maxwell picture, and this is basically one of the ideas behind this collaboration with Xiaoming and Tom. What happens to this picture here when I add bending? So I get stability here, maybe weak, but what happens to the criticality associated with this point? That was the question we wanted to ask. And so, well, in the interest of time, I'll show you the results. So what happens is, so these curves off on the left are on a log-log plot meant to represent this. And if you change the value of the bending resistance, you get higher levels or lower levels of the linear modulus here. By the way, I should also emphasize, since next time I'm going to talk about nonlinear effects, and I'm going to go to finite strain, I just want to remind you, everything we're talking about here, in addition to being t equals 0, it's infinitesimal strain. This is all linear stability arguments, linear elasticity, as this Maxwell counting argument is. It's limited to linear. Infinitesimal strain. Okay, so now to just show you how critical they are, this is a measure of fluctuations. Now what are those fluctuations? If it's t equals 0, they're not thermal fluctuations. Those fluctuations are these non-affine deformations, okay? Now, I suspect you've seen in some of the prior lectures, actually, Andrea was sort of hinting at it. She was mentioning non-affine effects. These non-affine effects can look like a fluctuation, but they're static. And they're actually only in response to an applied strain. That's the other thing. So it's kind of weird fluctuation, but they play the role of fluctuations. Even critical fluctuations, they peak at the transition. So what I'm showing here, forget the data down here for just a moment. What I'm showing here is data that for the modulus which drops, and it's dropping according to this picture right here, but going down to a lower level here for these different curves, which is bending stabilized. That's the isostatic point. Now, it's plotted in a slightly funny way because we're taking a particular lattice, a triangular lattice, and diluting it, so P is the bond probability. So this happens to be 4, okay? Well, around here somewhere is 4. 2/3, basically, would correspond to Z equal 4 for a triangular lattice. And what's interesting is even though the bending rigidity has not only stabilized the system, it suppresses fluctuations. The system's no longer critical. I'm no longer we didn't plot it here, but if you were to plot the corresponding curves at kappa equals 0, you'd get something which just crashes right down to 0 there, okay? So just imagine that these curves crash down to 0 at about 0.66. So not only am I getting stability in what would be the floppy phase for the central force picture, but my critical point went away. There's nothing critical. These are just smooth curves. Yeah, the curves show some maybe dramatic signatures here, but that's exactly what would happen if you tried to study ferromagnetism and all you could do was study it at finite field. You'd never see the Curie point. You could get very close and you could infer all of the critical phenomena. You just wouldn't be able to go right through the transition, okay? Now, I would argue that is precisely the physical or physiological situation with these networks. You can't go to kappa equals 0. I can't take one of those biopolymers and magically make its bending resistance vanish. It can be small. So anyway, this is one reason why we looked at this, to sort of look at the effects of Maxwell with bending. We get some interesting exponents. They happen to be non-mean field. I won't dwell on that too much. But what's nice on the right-hand side here is that you do indeed see scaling of the kind which, well, something like this. Yeah, question?
I mean, but there's another.
Yeah, sorry.
So that's a separate.
Yeah, so if I add bending energies to the Maxwell picture, I change the way I count constraints. I get stable networks, possibly at a lower modulus, by the way. By the way, the Maxwell argument only says 0, non-zero. Doesn't say anything about the magnitude of the modulus. If it's non-zero, it's rigid. If it's 0, it's floppy. So there is another transition, and it's rigidity percolation with bending. And so that's what's happening at this lower point. We studied both in this paper. That happens at this lower point, and notice that there's peaking fluctuations there too. So they're both critical, and I'll return to more of this next time with finite strain to see what happens. That's going to be very important for understanding that nonlinear mechanics of collagen I started with, the earlobe pulling experiment. But just before wrapping up today, I want to talk about this a little bit. So what that is showing, and this will be something I can wrap up with, but let me just sketch the results. I guess I can get rid of this. So I just want to quickly show you the kind of scaling ansatz we try and confirm over there. So the pure Maxwell part, pure central force, has a modulus which grows above the isostatic coordination number with some power law because it's going continuously to 0. So that looks like this. So basically it's saying that there's some power law of what I'll call delta Z when it's positive, which looks like that. Okay, that's just a postulate. If you measure that f exponent, a mean field model you'll find here that Tom and Jiaming worked out gives 1. The simulations show a value definitely different from 1, like 1.4. So it's non-mean field. That's interesting. So let's see. The actual modulus is this. I'll put back in my affine one. That would be what happens when I go way out here at large coordination number, highly connected structure, pure stretch. I might need to change what I mean by rho, the density of fibers in that limit, but it's basically this model. And then we've got some function, scaling function, of an argument, which is what? Well, this. Okay, what's kappa tilde? Well, kappa tilde is the natural dimensionless measure of bending rigidity, which is the following. I take the ratio of bend to stretch. That has units of length squared. So I divide out by the architectural length, LC squared. That's a dimensionless quantity. And if you plug in what this looks like, it's Young's modulus times a to the 4 naively for a fiber, divided by Young's modulus a squared for the stretch modulus, 2 factors of LC squared. Notice this is just a over LC squared, which I've argued several times is essentially the volume fraction. Okay? So the natural dimensionless measure of bending rigidity is just the volume fraction. And at volume fractions of order, 10 to the minus 3, 10th of a percent, it'll correspond to one of those curves there, I guess the light blue one. And this function here, f, as a function of its argument, x, it's a universal or not universal, but scaling function. And it's a scaling function that has limits of 1, or essentially order 1, in the region above the transition. I'll call that plus. Above the transition is high connectivity. Low connectivity will be minus. That's the minus region. So this is expected to be a linear function of x because x is kappa tilde over delta z to some power. And so that function on the right basically shows you these, okay? With a slope in between, which is the ratio of f to phi. Mean field suggests that should be a half. Simulations show it slightly different from a half. Again, non-mean field, maybe shouldn't be too surprised. Okay, so that was a fun little extension, if you like, of these Maxwell argument ideas to include bending. Let me just do one, I'll just draw a phase diagram, an overall phase diagram that sort of unifies essentially everything I've been talking about so far, and then continue next time. So the phase diagram is the following. Connectivity. I want to include this magnetic field. So this would be like temperature and magnetic field in a ferromagnetic context. There's some isostatic point here. So what happens? Well, at kappa equals 0, I've got a critical point here. This is genuinely critical. Put a big dot there. At any finite kappa, it's not critical. However, notice those decreasing functions. They're pretty steep near the transition. So you could call that a critical region because they also have peaking or diverging, technically, fluctuations. So you actually get a picture like this with a region which is critical. So you can still see the effects of criticality, even though you don't go through this transition. Again, if you're limited to live with these fiber systems at finite bending rigidity. Over here, the modulus is proportional to mu rho, i.e. 1 power of volume fraction. Down here, G goes like phi squared. It's that low modulus of this picture until I extend the fiber length. So as I indicated, there's this non-affine length lambda. I could go to high molecular weight. And even if I go out here, way down here, or way in front of this original 2D phase diagram, I would get G, again, proportional to mu rho. That's the high molecular weight affine limit. So that's what happens to this. I get a crossover from this weak modulus to a stiffer one. It's all linear elasticity still. There's actually a phase boundary over here, which is that lower connectivity point. Below that, there's no modulus at all, ever. G equals 0. And of course, if kappa gets really large, if this dimensionless measure of kappa gets large, I suppress all bending, and I just go back to a G proportional to mu rho. I still have my stretching. So basically, this regime extends all the way over here, with only over here this weak regime, a critical zone, and critical zone, and then at high molecular weight, this stiffens. Okay? Now, what I want to show you next time is what happens if I now also consider straining the system to finite strains. That also has an interesting effect on this. Okay? Sorry, I guess I'm a couple minutes over. Yes?
The lines you separating scaling sharp lines?
No. So there's no phase transition here at all. It's a region. So you should think, if I move through this region, all I see is one of those continuous curves, but with a range of signatures reminiscent of the criticality. Rather than a drop of the stiffness to 0, it's a rapid variation of it. And yeah, so I don't want to dwell on the shape of this too much, but it's probably more like this. But it's a little ill-defined because, yeah, the critical zone, you can see those curves there. As I go to higher kappa, they spread out more. So it looks like this is spreading. But also, at some point, the drop in modulus is getting small. So this upper boundary gets fuzzy, too. Okay, but it's not a phase. The only genuine phase transition is that point. Sorry? And the other one, yeah. Both of them, but this is the stuff I want to focus on, basically. Yeah, I'm going to continue to be inspired by Maxwell and focus on that, yeah.
But do you get similar scaling functions for the rigidity percolation?
No. So in that paper, and I've forgotten the values, I have a terrible memory for numbers. What I can tell you, just because I reminded myself recently, this F exponent, mean field is 1, 2D is 1.4, plus or minus error bars, which are small compared with 0.4. And in 3D, slightly bigger error bars because it's harder to do big systems in 3D, it's 1.6. So interestingly, it's non-mean field even in 3. That has implications for the upper critical dimension for phase transition fans. Unlike jamming being mean field by all accounts. These are different. But then if you go to the rigidity percolation point, those exponents change even more. And I'd have to look them up.
But, so you do get scaling for just different exponents?
Oh, no, sorry. This scaling analysis we only do near this point. Right here I get critical exponents still, but I'm not arguing there's a critical zone that spans that boundary. There's really nothing mechanical over here. But I do still get an F exponent because I get the dependence of the modulus with a power of z minus a lower threshold here, and the exponent, if I remember correctly, is like 3.5. It's big. Anyone know the number offhand from other? This is the kind of thing which is studied in rigidity percolation previously. So this part is not as new, at least as of, what, 10 years ago, new. These things are always relative. Yes? So what's happening in that region is, as you deform the system, and maybe next time I can include a sort of cartoon to show this. I think it'd take me a little while to get it now. But in that region, as you deform the system, you get non-uniform deformations. Those are the non-affine deformations. What's interesting is not only do they grow in magnitude at this transition, as you approach it this way or that way, they grow, that peak grows. You might be able to make out the peak is suppressed as you go to higher bending rigidities. It's also suppressed by finite size effects, normal critical phenomena. But what I wanted to also mention is what's more subtle is the range of correlated fluctuations grows. There's a correlation length which grows. So what you should imagine is when I get near this point, even at finite kappa, so somewhere down in here, as I move through this region, I'm finding massive regions of the network undergoing significant deformations. That's also a bit different from what Andrew was just telling us about, local rearrangements, for instance, in a glass, right? It's partly because of this network, this architecture with potentially long fibers that you get some long-range effects, which are different from jamming. Of course, in jamming, you also get a divergent correlation length. But
I have a question connected to the previous lecture. When you started saying that we have all these in the tissues and biological systems and so on, is there hope for those type of experiments for this type of ideas in the experiments? And then, if it's possible, is it important the longer range interaction that would be implied by the charges in the system, or?
I'll show several experiments next time.
Okay.
Yeah, so not this picture. So I would argue this picture doesn't necessarily apply for 3D network. By the way, we live in 3D, right? So, 2D is fun, arguably more fun for theorists. But in 3D, because of this much higher isostatic threshold, this physics doesn't apply. I will show that if I bring out not a molecular weight axis here, but a strain axis, I will find a transition. This is jumping ahead to next time. That transition has been studied experimentally with very good agreement. So that's next time, okay?
Okay, let's thank Fred.